Welcome to The Explainer. Today, we are diving into a concept in C++ that's basically a superpower, polymorphism. It's this amazing idea that allows one name to have many different forms, and honestly, it is the secret sauce for writing some seriously smart and flexible code. So let's kick things off with a little puzzle. How can the same exact command, say, speak, tell a dog to bark, a cat to meow, and a duck to quack? How can one instruction lead to so many different results? Well, that is the exact problem that polymorphism is built to solve. And the answer is polymorphism. The name literally means many forms, and that's precisely what it delivers. It lets you have a single interface, like one function name, that can trigger a whole bunch of different actions, all depending on the context. This is what makes C++ so incredibly dynamic. But hold on. To really get our heads around the magic of polymorphism, we first need to master the tool that makes it all possible, the pointer. So let's do a quick deep dive into what they are and how they work. Okay, so what in the world is a pointer? At its core, it's actually super simple. A pointer doesn't hold data itself. It holds the address of where that data is stored. Think of it this way. A pointer isn't the house, it's just the street address for the house. Let's make this real with an example. Say we create a simple integer variable, a, and we set its value to 25. The computer tucks that number 25 away somewhere in memory. For the sake of argument, let's just say it's at memory address 1000. Okay, next up, we create a pointer named p. Then we write this line, p equals and a. Now, that little ampersand symbol, and, is key. It means the address of. So p isn't storing the number 25. Nope. It's storing the number 1000, which is the address where 25 is living. This little table here is your cheat sheet for pointer syntax. We've seen the ampersand and, which gets an address. Now look at the asterisk, star. This is called the dereference operator, and it does the exact opposite. It says, hey, go to the address I'm holding and tell me what value is there. So star p goes to address 1000 and fetches the value, which is 25. All right, so we've seen how pointers work with simple numbers, but let's level up. What happens when we use them with something more complex, like an object? This is where their true power really starts to shine. Now, here is a really important detail. Normally, you'd access something inside an object using a dot, right? Like myObject.getData. But when you're working with a pointer to an object, you switch to the arrow operator, ptr arrow getData. It's a tiny change in syntax, but it's a huge signal that you're dealing with a pointer. And here's a cool little behind-the-scenes secret in C++. Whenever you're inside a member function and you access a member variable like mark, the compiler is actually doing something for you. It's secretly using a special pointer called this to refer to the current object. And this pointer is super useful. It's how an object knows how to talk about itself. It helps clear things up when a function argument has the same name as a member variable, and it even lets you do cool things like chain method calls together. It's a real workhorse. Okay, so we've got pointers and we've got objects. Now, let's mix in another key C++ idea, inheritance. This is where things get really interesting, and it's where we're going to see the need for polymorphism come into sharp focus. So one of the most powerful things about C++ inheritance is this. A pointer to a base class can also point to an object of a derived class. This is awesome. It gives us a ton of flexibility, but it also opens up a really important question. So here's the scenario. We have a base class pointer, but it's pointing to a derived class object. Now, what if both the base class and the derived class have a function with the exact same name, show? When we call bptr.show, which one runs? The base version or the derived version? And the answer, by default, might surprise you. C++ does what's called early binding. This means that when the code is compiled, it only looks at the pointer's type, which is base. It has no idea that at runtime, it's going to be pointing at a derived object. So it calls the base class's function. Now, that default behavior isn't always what we want. We want the program to be smart enough to call the function that belongs to the actual object. So how do we do that? Well, this is the moment we unlock true runtime polymorphism. The solution comes down to a single, incredibly powerful keyword, virtual. When you mark a function as virtual in a base class, you're essentially telling C++, hey, don't decide which version of this function to call just yet. Wait until the program is running and see what the object's real type is. Just look at the difference here. All we did was add that one word, virtual, to the show function in our base class. And that one word changes everything. Now, instead of making the decision at compile time, C++ waits until runtime, checks the actual type of the object the pointer is pointing to, and calls the right function. It calls the derived classes version. And there it is. That's polymorphism in action. The exact same line of code, ptr-show, now does different things depending on what ptr is pointing to. If it's a div1 object, it runs the div1 function. If we point it to a div2 object, it runs the div2 function. How cool is that? Now, this ability to make decisions at runtime is not just a neat trick. It's the foundation for some really advanced and powerful programming techniques. Let's just quickly touch on a couple of them. So sometimes your base class is just a concept, like shape. You can't really draw a generic shape, right? By making a function pure virtual with that equals 0 syntax, we create what's called an abstract class. It's like a contract. It says you can't create an object of me, and any class that inherits from me must provide its own version of this function. Pointers also give you direct control over your computer's memory. Using the new operator, you can create objects on the fly whenever you need them. But remember, with great power comes great responsibility. You have to be sure to delete that memory when you're done with it to prevent nasty memory leaks. So, if you take away just one thing today, let it be this. That virtual keyword is like a switch. It flips the decision-making process from compile time, where everything is based on the pointer's type, to runtime, where it's based on the object's actual type. And that shift in thinking is a complete game changer. It lets you write code that's way more general, way more flexible, and ultimately way more powerful. You stop thinking about what an object is and start thinking about what an object does. And believe me, that simple change opens up an entire world of possibilities.